welcome back. It's Pi, and today we're going to be taking a look at our 2021 AMC 10A debrief. And so we're going to be doing problem 12, and this is a geometry problem. So we want to know right off the bat, when I'm reading two right circular cones and with vertices facing down, as shown in the figure below, contain the same amount of liquid. So when they're containing a certain amount of liquid, I know I'm looking at volume. So let me just write down the equation for volume of a right circular cone. And it's always helpful to refresh volume and area and perimeter equations just before you get into the AMC 10. So it's going to be 1/3 pi r squared h for the volume of a cone. So we know the radii of each of these cones, and remember, they're not the base radii all the way up here, but they're the radii right when that water is filled up to that level. So over here it's going to be 3, and over here it's going to be 6. So for V1, I'm going to say that's 1/3 pi 3 squared h1, because remember, this height is going to be h1, which is different from that height. So let's take a pause and let's look at the relationship between the heights. So when I'm writing out volume 2, I'm going to be using H2 instead of H1. And that's because I know the bigger the base radius, the smaller the height. And that just makes logical sense, because if they contain the same amount of liquid and there's a bigger base area, and there was also the same height, then one of them would have more volume than the other, which doesn't really make sense. So we're going to plug this in, 1/3 pi 6 squared, and this time that's why I'm going to be using a different height, H2. Okay, and from what we just talked about, I know H2 is going to be less than H1. Moving on, into each cone is dropped a spherical marble of radius 1 centimeter. Boop. There's 1 centimeter, and they're the exact same volume. So the change in volume is going to be the same. And remember, the initial volume is going to be the same, and the final volumes are going to be the same. Okay, so this sinks to the bottom. It's completely submerged and no liquid is spilt, but that means the height does rise. So the height might rise up until here. And when the height rises, there's a new radius. So it's no longer the same radius, and that's going to happen in cone number 2 as well. Okay. What is the ratio of the rise of the liquid level in the narrow cone to the rise of the liquid level in the wide cone? So if I call this delta H1, I call this delta H2, this is the change in H1 and the change in H2. We want to find delta H1 over delta H2. And even looking at the answer choices, we see that if H2 is greater than H1, then the change in H1 is going to be greater than if H2 is less than H1, my bad. The change in one of them is going to be bigger than the change in the other, and that's just because the smaller the radius, the larger the height. So I can intuitively cross off option A, but we're left with the rest of these where it shows that delta H1 is greater than delta H2. So how do we go about this? So the first thing I'm going to do is realize that since the volumes are equal, I can just set these equal to each other. So I'm going to say that's 3 pi H1, which is equal to 12 pi H2. Canceling those pi's, common factors, and I get H1 equals 4H2, or H1 over H2 equals 4. Okay, so now I know the ratios of the initial heights, and I want to find the ratios of the final heights. So how can I use this information to help me? In the next step of the problem, let me clean everything up. Okay, so in the next step of the problem, what I want to do is I have those cones, and I'm going to say that if the initial radius was 3 over here, and this was the initial height, then the final radius is going to be something like that, and the final height is going to be over here. And so if this was 3, I'm going to say it got scaled by a factor of x, so it's x times bigger. So let me say this is 3x, and now x is going to be greater than 1 because the radius is only getting bigger. So this is h1, then I'm going to call this h1x, and that's because the scale factor that the radius grows by is the same scale factor that the height grows by. So my new bases are going to be 3x for the radius. And then for the wider cone, the radius is going to be 6y. So I'm going to apply the same principle. I'm going to say if my final radius is something like this and my final height is something like this was initially 6, this is initially h2, they're getting scaled by a factor of y. So this is going to become 6y and this is going to be h2y. So the final height is going to be h2y and the final height is going to be h1x. Okay, so let's take a look at final volumes. So the final volume of 1 is going to be 1/3 pi 3x squared h1. The final volume of 2 is going to be 1/3 pi 6y squared h2. So I'm going to get 3 pi h1x cubed and 12 pi h2y cubed. All right, so remembering that the final volumes are equal to each other, I can just set these equal to each other and again cancel common factors, and I'm going to get that x cubed equals y cubed, or x equals y. Okay, so let's go back to what we had initially. And so all we know right now is that the scale factor, the ratio of the change here, is equal to the ratio of the change, the scale factor that this increased by. So now what I want to know is the final heights, so the ratio between the final heights, or the change in heights rather. So I'm going to say I want to know delta h1 over delta h2. And delta h1 is nothing but the final h1 minus the initial h1. So h1x minus h1 over h2y minus h2 equals h1x minus 1 and h2 times y minus 1. I just factored over there, and remember x equals y, so these are just the same thing. If I cancel them, I get that the ratio between the changes is the ratio between the initial heights. And earlier, I figured out that h1 over h2 equals 4, and I figured that out by setting the volumes equal to each other. So really, that ratio we had earlier ends up being the answer.